Welcome to this online lecture for week 6 of Research in the Health Sciences. Today's class covers measurement reliability, measurement validity, and data collection techniques. This slide contains an image of an archery target at which arrows are being shot. This is a visual representation of reliability. The arrows are landing all over the target, not all hitting the bullseye. Is this a representation of good or poor reliability? Take a minute, pause the video, and think for a moment about what you understand about reliability. When you're ready to move forward, press play. This would be a representation of poor measurement reliability. We'll talk more about this moving forward. I will now guide you through an activity that is designed to help you understand measurement reliability. There are 2 accompanying documents that I have uploaded to Blackboard under Course Documents. The first is a PowerPoint file titled Reliability Activity. The second is a Word document titled Measurement Reliability Activity. Please pause the video and download and open these files now. Print the PowerPoint slide. Press play once you have printed the PowerPoint slide and opened the Word file. The PowerPoint file that you printed should look like this. Now that you have your PowerPoint slide printed and Word file open, I will read the instructions for this activity, which also appear on the slide. A reliable instrument is one that is consistent in what it measures. If an individual scores highly on the first administration of a test, for example, he or she should, if the test is reliable, score highly on a second administration. In this activity, you are going to evaluate the reliability of an instrument. Imagine that you are contracted by an employer to conduct a vocational evaluation of 13 different potential employees. You develop a 30-point test and distribute it to a pool of candidates in August of 2015. You then give the test again 1 month later to the day in September 2015. No services are delivered between the 2 times when the test is administered that you would expect to influence the scores. The scores of the candidates on the 2 administrations of the test are listed below, shown below on the actual handout of this reliability activity. Plot each pair of scores on the bar chart provided. That's the PowerPoint slide that you printed. I have entered A's scores for you to get you started, so that's quote-unquote student A. What does this graph suggest to you about the reliability of the success assessment? Explain. Apologies. Pause the video now and plot the scores on the graph provided on your PowerPoint slide. Once you are finished, press play. Looking at the graph you have created, what does this graph suggest to you about the reliability of the instrument you are using for this vocational evaluation? Do the scores from time point 1 to time point 2 for each individual seem to be consistent, or have they changed substantially? We will revisit this activity after reviewing some material on measurement reliability. This slide contains an image of a figure lifting a barbell weight over its head. Your text provides an example of measurement reliability. The example is as follows. A researcher is interested in determining whether quality of life for depressed adolescents can be increased through an experimental exercise program. Both the experimental and control groups received the pretest and that measures quality of life. Then after the 6-month intervention period, they received the same instrument on the post-test. The researcher hopes that the post-test scores from the experimental group are higher than those of the control group. If Jones scores 49 on the pretest, then our observed score is 49. If we were to give Jones the quality of life measure a second time, her observed score would probably be different, maybe 53 or 43. If we give the quality of life measure a third time, the score probably will be different from either of the previous scores. How will we know whether the change from pretest to post-test is due to the intervention, so systematic variation, or to something else? What is the main concern here with the quality of life measure? The issue here is whether the quality of life inventory will measure quality of life consistently, reliably in this study with this group of participants. This slide contains two images. One at the top that shows a test representing an individual's observed score, X, and on the right a cloud says T plus E. Boxes above the image say observed score equals true ability plus random error. The image on the bottom of the slide illustrates the relationship between reliability and error. On the left is a set of two circles that illustrate a reliable measure. There's a large white circle with a small gray circle within it. The large white circle is labeled error, while the gray circle within it occupies about 75% of the area of the white circle and is labeled true score variability. This shows that the error makes up a smaller portion of the measurement variance, which is the entire circle. Than the true score variability. My apologies. This would be a reliable measure. The image on the right is again of a white circle with a smaller gray circle within it. The difference between this image and the image on the left is that the gray circle occupies a small portion of the white circle, approximately 25%. The white circle is again labeled error, and the gray circle is labeled true score variability. This would be an unreliable measure, as the error makes up more of the variance than the true score variability. According to classical test theory, an observed score is made up of a true score and error. If we could subtract the true score from the observed score, we could determine how much of the score is due to error. We never actually know the amount of the observed score that is due to the true score and the amount that is due to error. To minimize error, however, we should choose a test with strong evidence of reliability. The higher the reliability of scores on an instrument, the closer the true score will be to the observed score for that instrument. This slide shows the bar graph that you should have created as a part of the reliability activity. It also shows two other types of graphs. On the bottom left is a line graph with two lines, one representing the time 1 scores for each participant and the other the time 2 scores. If the participants had scored the exact same on the measure from time 1 to time 2, these two lines would be completely overlapping. They do not. This means that the measure is not perfectly reliable. No measure is. We will discuss what is good enough, quote unquote good enough, when it comes to reliability. The graph on the bottom right of the slide is a scatter plot of the time 1 and time 2 scores. The blue dots represent time 1 scores for each participant, and the red dots represent time 2 scores for each participant. If the participants had scored the exact same on the measure from time 1 to time 2, the blue and red dots would completely overlap. Again, they do not, indicating that the measure is not perfectly reliable, but is it quote unquote good enough? The correlation coefficient, often used to evaluate reliability, is usually expressed as the letter R and indicates the strength of a relationship. The values of R range between -1 and +1. A value of 0 indicates no relation between two variables or scores, whereas values close to -1 or +1 indicate very strong relationships between two variables. A strong positive relationship indicates that people who score high on one test also score high on the second test. To say that a measure is reliable, one would expect a coefficient between +0.7 and +1.0. Others have suggested even stricter criteria. For example, reliability coefficients of 0.8 are acceptable for research, but 0.9 is necessary for measures that will be used to make decisions about individuals. For example, instruments such as IQ tests and those for personnel decisions. However, it is common to see published journal articles in which one or a few reliability coefficients are below 0.7, usually 0.6 or greater. Although correlations of -0.7 to -0.1 indicate a strong negative correlation, They are totally unacceptable as evidence for reliability. Such a high negative correlation would indicate that persons who initially score high on the measure later score low and vice versa. A negative reliability coefficient indicates a computational error or terrible inconsistency. I have uploaded another document to Blackboard under Course Documents titled Reliability Activity Excel. Please pause the video, download this Excel file, and open it now. Press play when you have done so. This slide shows an image of an Excel file with the left containing a table with 3 columns. Column A contains the student ID, letters A through M. Column B contains the Time 1 test scores for each student or worker, and column 2 contains the Time 2 test score for each student or worker for this vocational evaluation example. In order to calculate the correlation between the Time 1 and Time 2 scores in Excel, you would click in an open cell on the Excel file, and then click on the button in the top menu bar that is labeled Function Formula Builder. You would then select the function for correlation, which is CORREL. A box will appear with array 1 and array 2. You will then click in the array 1 box and highlight the scores for time 1. Then click in array 2 and highlight the scores for time 2. Hit enter. The score that is calculated is R, the correlation coefficient. If you've done this activity correctly, this should read 0.87 approximately. This indicates good reliability. The message here is that we can't necessarily rely on the graphs to indicate whether a measure is reliable. If you looked just at the graphs, you may have thought the measure had a lot of inconsistency, but in actuality, it has good reliability. This slide shows a chart on the top with a perfect positive correlation in Excel. The lines are parallel to one another. The chart below is a line graph of the data we used for our activity. The lines are not perfectly parallel. Again, we need to look at the correlation coefficient to make judgments about the reliability of a measure. So what are the different types of methods we might use to assess reliability? Pause the video for a moment now and see if you can recall from your reading in the videos that you have watched this week. Press play when you're ready to move on. Test-retest reliability, sometimes referred to as a coefficient of stability. Test-retest reliability is the most common method to assess reliability over time. This is what we just experienced in the activity. There's some points to consider regarding test-retest reliability. Test-retest reliability is not established during a study. It must be established when little related to the substance of the instrument should be happening between the two administrations. This is especially important regarding experiments with children where developmental changes between the two administrations of an instrument could alter test-retest reliability. With standardized instruments, evidence for test-retest reliability usually has been obtained, although not necessarily with the population of interest. The sample used to establish evidence of the reliability of the instrument should be similar to the sample used in the study. The length of time used to establish evidence of test-retest reliability is usually short, but for use in experiments, it should be similar to the length of the intervention to be used in the study. Note that as the length of time increases between administrations, the reliability usually decreases. Another form of reliability is parallel forms reliability. One of the problems of using the same instrument for the pretest and post-test of a study is that participants may use knowledge gained on the pretest. In this situation, often referred to as testing or carryover effects, it's impossible to determine whether the change in scores is due to the intervention or to knowledge obtained from the pretest. Some standardized tests have a second or parallel form that could be used as a post-test in place of the instrument that was used at pretest. Parallel forms reliability, or the coefficient of equivalence, involves establishing the relationship between the two forms of the same test. This method involves having a sample of participants take both forms of the same instrument, usually with very little time elapsed between administrations. Then a correlation coefficient is computed for the two sets of scores, which should be at least 0.80 for parallel forms reliability. Another form of reliability is internal consistency. Often the researcher wants to know that the several items within an instrument are consistent. Are they measuring the same thing? The investigator can use the results of a single administration to determine internal consistency. The most common method for determining internal consistency is the Cronbach's alpha, often referred to as a measure of inter-item reliability. So it's not actually really are they measuring the same thing, but are the items all measuring consistently across time. Inter-rater reliability is another form of reliability. When observation is the instrument, inter-rater reliability must be established among the judges. Although there are numerous ways to determine this form of reliability, the common theme is that two or more judges observes and scores certain episodes of behavior, and then some method of assessing an agreement is formed. We will now transition to talking about validity. The image on this slide shows a bowling ball hitting the head pin and knocking down all the pins for a strike. The text on the ball reads, "Validity, are we hitting the head pin?" This is a visual representation and metaphor for validity. In bowling, we are aiming for the head pin. In research, we are aiming to quote-unquote hit or capture a certain construct. We want a measure to be valid for a given population and for a specific purpose. For example, specialty area scores on the graduate record examination might be used to predict first-year success in graduate school. However, they also could be used as a method to assess current status or achievement in a particular undergraduate major. Although the same test is used in both instances, the purpose of the test is different, and thus the evidence in support of each purpose could be quite different. So what are the 5 broad types of evidence to support the validity of a measure discussed in your text? Pause the video for a moment and see if you can recall. Press play when you're ready to move on. The 5 broad types of validity discussed in your text are content, responses, internal structure, relations to other variables, and the consequences of testing. The slide contains an image of a triangle. What is, quote-unquote, the Trinity view of validity? Pause the video for a moment and see if you can recall. Press play when you are ready to move forward. From 1966 until 1999, the standards included the so-called Trinity view of validity, which categorized validity into 3 types: content validity, criterion-related validity, including concurrent and predictive methods, and construct validity. However, the 1985 standards warn that the use of the labels content, criterion, and construct should not lead to the implication that there were 3 distinct types of validity. Increasingly, validity has been conceptualized as a unitary concept. Many types of evidence may be gathered, but there are not many kinds of validity. This slide gives the current definition of validity according to the American Educational Research Association, AERA, and the National Council on Measurement in Education, NCME. The current standards describe validity as the degree to which evidence and theory support the interpretations of test scores. The standards went on to say that the process of validation involves accumulating evidence to provide a sound scientific basis for the proposed score interpretations. It is the interpretations that are evaluated, not the test itself. There's another document that I have posted to course documents on Blackboard. It is a Word document titled Validity Activity. Pause the video, download this file, and take a moment to complete it now. When you have finished, press play. Bring this activity with you to class next week, and we will discuss together. We should ask ourselves the question, can an instrument be reliable without being valid? This slide contains 4 images. The top left image shows a bunch of dots on a target. They are random and all clustered at the top of the target. None of them are in the bullseye. This represents a measure that is neither reliable nor valid. The dots aren't consistent in their placement, and they would not average together to equal the bullseye, what we are trying to hit, like the head pin if a measure is valid. The next image on the top right of the slide shows dots that are all over the target. So this represents a measure that is not reliable. However, if you average them all together, they would likely hit the bullseye. This would be a measure that is unreliable but valid. The bottom left image shows dots that are all clustered together on the target in one place, so this represents a reliable measure. However, they only occupy the small portion of the target, so the measure is not valid. The final image on the bottom right shows all dots clustered together on the bullseye, representing a valid and reliable measure. You should now open your research article, look at the methods section. What evidence for reliability and validity of the measures used exists in your selected research article? Pause the video and take a look at your article now. When you are ready to move on, press play. We will now review this together in class next week. Again, take a look at the methods section of your article. What data collection techniques were applied in your research article? Reference the data collection techniques table 10.1 from your text to help you decide. Thank you.